Lesson 28. In this lesson, we are finishing up example number 3, and we're going to see if we can move on from there. Now, you'll notice in the camera in this video here that I've got the camera focused on my calculator. Now, you'll also notice I have y1 equals sine of x. I have the original function plugged in. y2, the first polynomial, x. The third polynomial, this one plugged in. The fifth and the seventh as well. Now, notice next to the y's, there's a check mark for whether or not it's actually plugged in. Well, these two here will be graphed first. So what I'm going to do is I'm going to go ahead and hit my graph button. Now, there's a number of things you're going to want to make sure you have done before you hit that graph button. Otherwise, things are going to get screwy. Not to mention, I don't know if you have the certain setup in your calculator. So the first thing I'm going to do is I'm going to go to mode. Now, again, mine's a little bit different. I'm going to make sure my mode is on radian. If it's not on radian, things might get a little bit screwy. The next thing I'm going to do is when let me go ahead and escape that, Now, when I go to graph this, okay, I'm going to hit the zoom button. Now, for me, my zoom button is F2. For yours is something else. I'm going to hit the zoom button. Check to see, and I'm not sure if it's in the yellow calculators, in your calculators, check to see if you have a zoom trig. If you do, go ahead and hit that and see what happens. If you don't have that, zoom standard should work just fine. If not, play with the zoom in, zoom out functions until you get something that looks something similar to this. Now you'll notice there's y equals x, this line right here, and here's sine of x. Notice it's really accurate, almost between what? It looks like pi over 4 and negative pi over 4. Again, pi over 4 and, I'm sorry, not pi over 4, pi over 2 and negative pi over 2. Okay, it's really close between those values, otherwise it's completely off. So that's why we come up with the next one, again, the y, or P3. So I'm going to go back to my y equals, and I'm going to go ahead and turn this on. Now, for me, I turn it on with F4. You probably have to move over into that bar, that spot right there, and hit enter until it actually gives you a solid line of some sort. So I'm going to go ahead and view this on the same screen. So let me go ahead and go to the graph again. Those two have already been graphed. That is my cubic that approximates it. Now, it definitely doesn't go much further, okay, but the further it does go, it is definitely more accurate. So this is definitely much better. Let me go ahead and check the next one. And I suggest that you draw these images. Okay, I suggest that you draw these images. Now I'm going to turn that one on, and I'm going to look at the graph again. So I have the first polynomial, the third polynomial, the sine function, and there's my next one, where it's getting more and more accurate, again, here and right here. Okay, let me go ahead and look at the next one. Now, if we continue this process, you will see that over time, I didn't want to do that, that over time, it keeps getting more and more accurate. Now, this might start to be or it might start to look very, very convoluted. What I'm going to do now, okay, is you'll notice how it's getting more and more accurate. I'm going to go ahead and turn off the previous ones. So I'm going to turn off this one, this one, this one. And now I'm just going to look at the graph of those two. The original function, sine of x, and the seventh degree approximating polynomial. And you'll notice right around this loop right here, it's not very accurate. It's not perfect. But it's definitely more perfect than it was before, okay? And same with over here on this loop right here. It's definitely off by a little bit, but it's definitely more accurate than it was before. So this, you'll notice, keeps getting more and more accurate as we go along, okay? And that's the idea. Now, what I'm going to do is I'm going to zoom out of this, and we're going to go ahead and I'll show you these same images in your textbook. I do want you to go ahead and make sure that those are written in your notes. I want to see those in your notes. So the pictures are, again, on page 679, and I'm going to go ahead and see the best I can do this with the space that I have here. The images are at the bottom of the page. You'll see the first one is the linear one, okay? P1 is x. The next one is P3. P3 is this one right here, where it's got the cubic. The next one here is the fifth degree polynomial. Okay, it's getting more and more accurate. And then this one over here is P7. Now again, it might not show it as accurate as the calculator did, but this actually gets better, more accurate right around this hoop right here. Okay, so make sure you have those images drawn in your notes. Again, that's on page 679. And let's go ahead and return to the next thing in our notes. Now, the next thing in our notes is power series for elementary functions. Now, for this, I should actually keep the book close to me. I'm going to go ahead and pull that book back over here. That is on page 682 in your textbook. Now, it lists all of the types of power series. 1 over x is this particular series. It converges 0 to 2. 1 over 1 plus x is this particular series. Okay, it converges -1 to 1. Is only accurate between -1 and 1. We have natural log of x. We've done that one. We have e to the x. I don't remember if we've done that one. I'd like to say that we did. Sine of x we just did. Cosine of x. Remember how cosine and sine are compared. It's all about the derivative, right? The derivative of sine is cosine. What is the derivative of x cubed? Well, it's 3x squared. Doesn't the 3 in the denominator cancel out with the 3 in the denominator or numerator, and then isn't just x squared? So it's x squared over 2 factorial. And negative, negative, positive, positive. Derivative of this is 5x to the 4th. X to the 4th, the 5's cancel out, left with 4 factorial. The derivative of this makes sense. It still applies. Okay. We also have arctan, somebody drew in this book, arcsine, and this 1 plus x to the power of k. And we have all of the convergences, or intervals for those. Okay. Notice the intervals for e to the x, sine of x, cosine of x are perfect every time. Okay. So that covers, again, make sure you have that elementary functions written in your notes. I do want to see those. Those are very important. We will use those again and again and again, just like we will right now. So example number 5. This is find the power series for f of x equals to the cosine of the square root of x. Now you're thinking, I do not want to take those derivatives. And you know what? Neither do I. Okay, those are not going to be fun derivatives to take. You have to apply chain rules. I mean, let's just show what we would have to do. We'd have to first start, okay, f prime of x is equal to. I have to take, this is the inside of the function, okay? I'd actually have to take the product, or sorry, not product, the chain rule. So the derivative of cosine is negative sine of the square root of x left alone. And the derivative of the inside, the derivative of square root is x to the 1/2. Derivative of that is going to be 1/2 x to the negative 1/2. And this does not get pretty at all. At all. That's just the first derivative. Let's try the second derivative. No, I'm just kidding. Let's not. Okay, I don't want to do that. That's a lot of work, and it's completely unnecessary. Let's start with this. Cosine of x. What is its power series? Well, if you didn't have a chance to glimpse it, okay, the cosine power series is actually similar to the sine power series, except for we're looking at all the even terms. So 1 x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus dot, dot, dot. Again, this continues on forever. This is the cosine, okay, power series. Well, if this is the cosine power series, what's the cosine of the square root of x? And again, this is perfectly equal to. Not approximated, not good enough in some locations. No. The interval of convergence on this was between negative infinity and infinity. Okay, this is a perfect convergence for cosine. So if I plug in the square root of x, what does that do? Well, if I legitimately plug in the square root of x, I get this thing here. Now let me simplify those things. This is equal to 1 minus, well, the square root of x squared is just x over 2 factorial. This thing becomes, well, isn't that just x squared then? So plus x squared over 4 factorial. Minus, this becomes x to the power of 3 over 6 factorial. And let's just throw in the last one, or another one just to make sure. 1, 2, 3, power of 4, and then this would be 8 factorial. If you wanted to, you can legitimately write this out as a series. We don't need to, okay? Now, the question is, this series up here converge for negative infinity to infinity. Where does this one converge to this? Well, let me ask you this question. For what x values is this even possible? As long as x is not negative, this is okay, right? Again, as long as x is not negative. So really, my convergence is for x greater than or equal to 0, because it has to be positive. Okay? Again, it's because the square root of x, you can't plug in any negative numbers, so this is only the set of numbers that I can plug in. This is what I was looking for. So I have that as my final result. Okay? Again, make sure you do identify where that particular thing is convergent.